In 1989, Nintendo brought a paradigm shift to the world of portable gaming, and that was the Nintendo Game Brick. And that was the Nintendo Game Boy. With new and advanced features like a 2 MHz CPU, 4 channels of stereo sound, and a 160 by 144 mucus-colored dot matrix display, this thing kinda blows. Okay, hear me out. It was 1989, and there was better LCD technology than this on the market, definitely. Not even LCD stuff, like, how about a screen like this in the Sony Watchman? Sure, it's a CRT and consumes more power, but it's got a comparable display size, it's much brighter, and it has better contrast. I mean, you're only talking about like 4 shades of gray on this thing, so. Display quality wasn't really the name of the game for, well, the Game Boy. Nintendo designed this thing to have a long battery life and to be made down to a price point. It's super cheap, so kids could afford it. Go figure. But from a hacker's point of view, its simplicity is a virtue. It's pretty easy to understand. It's got a really simple 8-bit architecture. It's easy to program. There's not a whole lot going on with it. Which leads me to the final leg of this tangent. We're gonna plug it into my car and make the world's worst digital dash. Because why not? Man, when I started out this project, I just wanted to learn how the CANBUS works, so I just grabbed the thing closest to me on my desk and went, okay, Game Boy it is. You could probably like display miles per hour on here and write some code for it to display things coming off like a serial port or through the card edge connector slot in the back. So yeah, let's dive into it. Hey, welcome back. So first and foremost, we're gonna do a little diagram on the chalkboard up here to give us a top-down overview on how the Game Boy car project's gonna play out. When's the last time you saw a car looking like that? Alright, so here we have our car. And inside the car, we have the CANBUS. Now, for those who don't know much about the CANBUS, it's a small local area network that lives within your car. Most computer equipment that exists within your car connect over the CANBUS, such as different sensors, your infotainment center, your ECU, and, well, your dash. Alright, just about every car has a wheel speed sensor, and this senses how fast the car is moving. This data is usually piped directly to your engine control unit, which is kind of like the CPU of your car, and then is broadcast over the CAN bus. Now your dashboard ignores most CAN messages, but when it sees something related to wheel speed, it'll pick it up, interpret it, and then display it on the dials in your dashboard. And there you go, you get things like speed, RPM, gear position, what have you. Now for the interesting part. Yeah, that should work. What I want to do here is create an interface board that works between the car and the Game Boy. Now, this board serves two functions. First, it receives data from the CAN bus and only looks for messages regarding speed. The second is providing code for the Game Boy to boot off of, so it's going to look like a normal Game Boy cartridge as far as the Game Boy is concerned. My idea for the code goes something like this. This is a memory map of the Game Boy address space, which the ROM usually occupies. This is usually all ROM space, so this is the read-only memory that your Game Boy reads to get all the game data and play your actual game. What I'm gonna do is trick it. Most of the code in the ROM is going to be general housekeeping. It'll tell the Game Boy like what to display on the screen and making sure it has a proper boot up procedure and all that. But then every once in a while, the code will read this little segment of the ROM down here. Basically, it thinks this address here is still part of the ROM chip. But when the Game Boy sends over the address data of, hey, I want to read this part of ROM, we'll have some circuitry over here that, instead of sending it the part of the ROM chip, sends it the data that's in the microcontroller. And then the Game Boy reads the speed data off the microcontroller instead of the ROM. Pretty clever, huh? So, just to run things through again one more time. The ECU reads data from the wheel speed sensor and puts it on the CANBUS. When a speed message gets transmitted on the CANBUS, our interface board will pick it up. The microcontroller on the board will interpret it and store it as an 8-bit value in here. Meanwhile, our code over here is going to be running in a loop and displaying what's ever at this address on the screen. Every once in a while, when it reads this address, we're going to do the bait and switch, and instead of giving it address 7FFF on the read-only memory, we're going to supply it with the 8-bit mile/hour value received and interpreted by the microcontroller. And our speed will appear on the screen. And now that we have all the theory out of the way, there's nothing left to do but build the thing. Come on, let's go. Okay, here we are back in the lab. I've got my pencil, paper, and Star Wars coffee mug, so let's get right into it. Now, there are three main groups of signals that we want to look for while interfacing with our Game Boy. First, we have our data bus, and that's going to be our 8-bit two-way street of getting data in and out of the Game Boy. Though, honestly, we're going to end up just getting data into the Game Boy, and the Game Boy's not going to send any data back. Next, we have our address bus, and we have A0 through A15, which means we have a 16-bit address space. The Game Boy changes these address lines from low to high, or vice versa, in order to select which address it wants to pull data from on our cartridge. Now, 16 bits of address space gives us 64 kilobytes of ROM to work with here, but we'll be using half of that, which means our maximum ROM size will be 32K. Here, let me explain. Taking a look at the memory map for the Game Boy shows us a 32 kilobyte user program area. Our program can start here at 150 hex, but only gets 32 kilobytes of space to work in, which means we're only using address lines A0 through A14. The rest of the memory map is occupied by components internal to the Game Boy, such as control registers, character data, and video RAM. This means for this project, we're just gonna forget about the A15 address line. We're not gonna need it. Last but not least, we have to worry about the control lines. The control lines read, write, and chip select are output from the Game Boy to our cartridge. Meanwhile, reset is an input in case you wanted to remotely reset the Game Boy. I will point out that all the control lines are inverted, so when the Game Boy sends out a read request, this line will be pulled low rather than going high. Really, the two most important ones here are the read line and the chip select line. First, the Game Boy sends out the chip select. Chip select goes high when accessing the ROM from your cartridge, and it goes low when accessing external RAM that might be present on your cartridge. Now, we won't have any RAM on our cartridge, so we're only going to worry about the chip select going high when accessing our ROM. After the ROM's been selected, the Game Boy sends out a read signal. Pulsing it low latches any bits that are on the data bus into the Game Boy, which means our chip select line's kind of like a, hey, heads up ROM, we're going to read ya, and then the read pulse is it actually reading data off the ROM. So, with all of this in mind, we're going to have to design two circuit boards. Board 1 will plug directly into the Game Boy and break out all of these data address and control lines. Board 2, on the other hand, will contain a ROM for the Game Boy to read, decode the addresses that the Game Boy is sending over, and when it sees that 7FFF address, send whatever data it finds on an 8-bit port over to the Game Boy. So now let's talk about all the actual chips and circuits that will go into these printed circuit boards. And it turns out, someone beat me to the punch in the late 90s. Yeah, this thing is like kind of the Bible for getting into designing peripherals for the Game Boy. If you just search the Game Boy project by Mark Rahr, it's like the first thing that pops up on Google. This was kind of my saving grace here. It was like the holy grail of cartridge information. It's got like a pinout of the card edge connector, and pretty much confirmed that you could just wire up an EEPROM to these pins and the Game Boy would read it. Now what we're looking at here is the schematic for the breakout board for the Game Boy. And yeah, it doesn't look like much. Basically, it consists of a 32-pin header and a custom connector, which is going to be a card edge connector for the edge of the PCB. Now, what I've done here is taken apart this Game Boy flash cart. I got my set of calipers, and once I got it open, I took my calipers and measured things like the spacing of the pins, how wide they are, the thickness of the board, the overall dimensions of the cartridge, and things like how deep the notch up top is set in. And with all the dimensions taken down, I've made a custom component in KiCad. KiCad? That's this edge connector at the bottom. I also did all the board outlines so that this thing should just slot into the Game Boy. Now, the PCBs I have aren't quite thick enough for the edge connector inside the Game Boy to make good electrical contact with the pins. So I've 3D printed this little spacer here to help guide the PCB into the Game Boy and to allow a tight fit between the edge connector inside the Game Boy and the PCB. The only downside about manufacturing this PCB at home is the traces have to have a minimum thickness in order to resolve properly. Which means you get this kind of goofy single line of wires up at the top, just because the traces can't go in between the pads. Would have loved to use a box connector. Would have made the whole thing a lot smaller. But getting back into it, we've kind of got the card edge connector figured out. So now we'll focus our attention on the interface board. Here's a basic logical layout for our interface board. All of our address lines get fed into our ROM. This allows our ROM to behave pretty normally and act like any other Game Boy cartridge. The ROM will also receive our read signal and our data bus from the Game Boy. Now, also attached to our address bus is this AND circuit. I think I'm going to have to cascade 2 8-input AND chips in order to accommodate our entire address bus. Basically, when this circuit detects that all of the address lines are pulled high, otherwise known as address 7FFF, it will send an inverted low signal out of this port right here. Now, since it will be normally sending a high signal, and our chip select is normally high when accessing ROM, these two signals get ANDed, which results in a true, inverted, which results in a false, and fed into our inverted chip select line, which again makes it true. It's kind of like a double negative there. Which is to say that if our chip select line is selecting a ROM and our address is not 7FFF, then the Game Boy will be reading off the ROM. I drew that wrong. Okay, did a little correction there. It doesn't affect what we've talked about so far, but it's going to affect this next part. Now, if we do detect address 7FFF, this ANDed circuit outputs a low no matter what, which means its inverted version outputs a high no matter what, which prevents the ROM from being able to put data on the data bus. Now, at the same time, this low signal we get from detecting 7FFF goes into the chip enable inverted for our buffer. This is an 8-bit parallel chip that will allow access to the bus. So when this chip enable is low, our door opens up, and our 8-bit data value that's gonna sit at this data in port will make its way onto the Game Boy's data bus. And that's gonna be the core of the interface board. Alright, now here we are back at the computer using KiCad. KiCad? Potato. And I've done a schematic of the interface control board here. We'll start out with our ROM chip here in the middle. That's connected to A0 through A14 of the address lines on the Game Boy. Most of the lines on the ROM will directly be connected to these connectors. We'll solder some wires in and run them over to the Game Boy. As you can see, all the address lines are connected directly to the Game Boy, and so are the data lines. We also have ground and VCC making their way over there. Write enable is tied to VCC, so it's permanently disabled. We don't want to write to our EEPROM. And everything's a straight shot except this chip enable pin right here. The chip enable line is being fed from our inverter here, and then further down the chain, this AND gate, which is, again, gonna select whether our ROM is being read or not, based on the chip enable signal coming from the Game Boy, and the output of our CD4068 8 input AND gates. You can see here how it's daisy-chained one to the other. You have one 4068 over here that's handling most of the upper address lines, and then that waterfalls into this 4068 over here, handling the majority of the lower address lines. We have our inverting output here that's fed to both our AND gate and our 8-bit buffer. Our buffer's input stage is right now connected to these dip switches, which I'm probably going to get rid of, only there for like testing purposes, and the output gets fed to these data lines. We've hardwired the direction so that data only flows one way through the data buffer. And last but not least, I added this little reset switch, so we can reset the Game Boy directly from the interface board. Now, one thing of note here, in terms of board design, you can see these jumpers. So, what gives? Well, as I've been designing the board, I've been switching between the schematic view and the PCB editor. I'm going to make this board from scratch at home, so I only have access to single-layer fabrication techniques for circuit boards, which means I have to factor in these jumpers in case a connection passes through a group of traces and needs to get to the other side. Here you can see one of the places where the signal has to get from this side of the board to the other, and I couldn't factor in a jumper. So there's going to be this long bodge wire from one end of the board to the other, and that just kind of sucks. But yeah, once again, we got the points where the wires are going to leave the board over here and go to the Game Boy. We got our EEPROM in the middle. We have 1 and 2 4068s. Little push button for reset. Got our AND chip and inverter chip. Our 8-bit buffer, the dip switch, which I'm going to just leave out. And the 8-bit data port that will connect to the Arduino. And that pretty much concludes the whole circuit design portion of the project, which means we're on to the next step, putting it together. First, we're going to prep these copper-clad boards with black spray paint. Lately, I've been having a bit of trouble with the toner transfer method from my previous videos on PCB manufacturing, so I'm going to try something a little bit different here. Next, we'll be using a laser engraver to remove some of the spray paint. My methodology is as follows. First, I take my design from KiCad and export the traces, copper pads, and board footprint to PDF. After that, I import the PDF into GIMP. From there, I crop it, invert it, mirror it, and then export it into that same PDF file. Finally, I import the PDF into Lightburn and export the G-code to run on my engraver. I find that a speed of 40 millimeters per second with a power output of 15% works pretty well with my longer Ray 5 10-watt laser engraver. Next, I mix up a solution of copper chloride and apply it to the copper-clad board. You can find some more information on this on my Etching PCBs video. After that, I'll wipe the board down with acetone, cut it to size, drill some holes, solder/populate the board, and that's it! Our Game Boy control interface is done! We have our card edge connector over here that runs along this ribbon cable over to the main control board that sends 8-bit data over to the Game Boy. Now we just gotta take our Game Boy here, insert our little plastic spacer into the back, plug in our card edge connector, and turn on the Game Boy. Oh no, we forgot the code! We forgot the code! Alright, so what do we have here? Well, basically it's a Game Boy flash card with an 8-bit data port sitting at the tippy top of our 32K address space. But we have a slight problem. No ROM. And obviously that means that we have no place to store code, which is why I'm going to be using one of these. It's a Zycore 28C 256 electrically erasable programmable read-only memory, or EEPROM. I'll just call it a ROM chip for brevity. Now, the way I'm going to be programming this ROM is with one of these. It's a USB EEPROM programmer. I think it's just a generic copy of a TL866 Mark II programmer, but it'll get the job done. Now, all I have to do is pop our ROM chip in here and go over to our computer. And yeah, I know, it's like a Windows XP VM. This actually is a disk image from an old laptop I had that had the XG Pro software on it already. So we'll be using that to program our ROM chip, but why not? Yeah, all I have to do is open our Game Boy file. Gets loaded into the buffer here. Just hit program. Just pop this into the socket. And yeah, it's that easy. That's how we're going to get code from our computer onto our Game Boy. Okay, now let's talk about the code. Trust me, I'm going to make this one simple. Alright, now who likes writing in assembly? Yeah, me neither. So we're going to be writing this one in C. Well, you know, the greatest programming language of all time. And for compilation, we'll be using the Game Boy Development Kit, or GBDK 2020. Anything can be written in C. Lights! Thank you. So first and foremost, we have our include statements. These are all the libraries and functions for GBDK. Next, we have two constants, X position and Y position. X position keeps the story moving forward, but together they'll make up a coordinate on the screen, which we'll get back to later. And now we get to our void main. The variable SW is cast as an 8-bit unsigned integer, and that's where we'll be keeping our miles per hour value. And this can be anywhere between 0 and 255. This other 8-bit unsigned integer value here, change, will hold an updated version of the mile per hour value and will come in handy later in the code. Next, we'll be creating a pointer that points to our 7FFF address here. Now, when we set our SW variable to our pointer at index 0, the Game Boy is going to read whatever value is at 7FFF and copy it over to our miles per hour variable. Now, we have this goToXY function here, which is going to put a cursor at position X, Y on our Game Boy screen, which at 6, 8 is going to be somewhere around here. And then we have this printf function. It's going to print miles per hour, and then sub in this U% with SW. Now for our last leg of the code, we got a while one here. It's an infinite loop. It's just going to run this bit over and over again. We're going to update SW again from our 8-bit address port. And if our SW value is different than our change value, we're going to our starting position and printing miles per hour with a whole bunch of spaces in it. That's because when the screen updates, it doesn't clear itself. So if you have a mile per hour value of 35, and then slow down to 8 miles an hour, that 5's still going to be hanging on there, so it's going to look like it's 85 miles an hour. So yeah, printing a bunch of spaces just clears this, bring it back to the start, and print your new value. Now finally, we set change equal to SW. This is so that if you're locked in at a constant speed, the Game Boy display isn't constantly updating. There's a little bit of flicker that happens when it does update, and that's very annoying. So we're going to try to mitigate it with only updating it when necessary. And there you have it. That's like the whole Game Boy program in 30 lines of code. Now it's just a matter of compiling the code with this magic line here, uploading it to the Game Boy's ROM chip, and we're off to the races, being able to display any data that's on that 8-bit port. This now leads us to the last major part of our project, which is decoding speed data from our CANBUS and sending it over to our Game Boy with a microcontroller. Now, in order to figure out which data corresponds to speed on our CANBUS, we'll have to do a little bit of snooping. With a pretty inexpensive tool, some free software, and a funky looking cable, let me show you how it's done. First, we have our USB CAN bus transceiver. On one end, we have a USB-C port, and on the other, we have CAN low, CAN high, and ground terminals. This one in particular is called Cannibal, and can be had for around $20 on eBay. The other bit of hardware we'll be using is our OBD2 cable. Our OBD2 connector here is broken out into 3 different wires. Pin 4 is our chassis ground, pin 6 is our CAN high, and pin 14 is our CAN low. Now, the CAN bus uses a differential pair as its transmission medium. Basically, both of these wires work in conjunction to transmit a signal, and both of them work in conjunction to receive a signal. It's not like one of these wires transmits and the other receives. It's like chaos on the CAN bus. If anything, I think it's more akin to early Ethernet with collision domains and a single medium that everything's connected to. I might be wrong on that, but either way, the interface only requires 3 wires. And now we'll just plug them into the CAN transceiver as it's labeled on the back. And now that we're all wired up here, let's talk about the software. But in order to do that, let's go out to the car, and I'll show you. Now, here I am over at my car. In the passenger seat, I have my laptop and my Cannibal interface board with my OBD2 connector. The first thing I'm going to do is plug my OBD2 cable into the OBD2 port underneath the dash. I think there's like a government mandate that states that the OBD2 connector has to be within 3 feet of the steering wheel or the driver or something. So most cars have it underneath the dash. All right, and it should be right under here. Here's my OBD2 port. It's right by the brake pedal. And I'll plug the connector right in here. Now you can see the cable going out and over to our CAN bus USB interface. Now I'll just plug it in via USB. All right, and our lights are illuminated. All right, now I'm going to open up SavvyCAN here and go over to the Connection tab. Open Connection window. I'll add a new connection device. I think Cannibal uses the SLCAN serial connection type. Now I just got to select the right COM port. Serial speed should be fine. Now our CAN bus speed should be 500,000. And we'll create a new connection. See up here, we're connected. Close out of that. But right now, we're not getting any CAN data packets, and that's because we haven't started the car. Start her up here. And I'll put SavvyCAN into overwrite mode. Yes. So right now, we can see all the data flowing over the CAN bus being received by the laptop. And here's what makes SavvyCAN such a great tool. We can mouse over to RE Tools, and choose the sniffer option. With the sniffer option selected, we can see all the data that changes on the CAN bus. You see, the CAN bus has thousands of messages that are transmitted over it every second. But what this data viewing mode allows us to do is look at only the data that changes. Although there's a lot of raw data that flows over the CAN bus, there are actually only a few addresses. Some of these addresses are only updated like once a second, where other addresses can have data that's updated hundreds of times a second. And this frequently updated data is what we're going to be on the lookout for regarding speed. Now, I don't know if you've been able to tell, but we haven't moved yet, which means our speed data hasn't changed at all. So, using the notch button, we're going to be removing the data that's been constantly changing this entire time. Hit notch again, a couple more times. Now let's put it into drive. Oh, and you can see some of the data has changed. This is probably RPM, gear shift data, what have you. All right, for this next test, I'm gonna drive extremely slowly. I'm gonna have the phone pointed at the dash, and we'll record a little bit of data. But yeah, gonna be extremely cautious and extremely vigilant. And let's start moving. Being cautious and extremely vigilant. All right, just turning around now. And yeah, I think I've only gone maybe like 75 feet down the road. All right, I'll stop collecting the data here. And yeah, there we have it. That should be enough data for us to determine which address has the speed data, and also which byte of data represents speed. Upon reviewing the data that we've collected about our CAN bus, it appears that packets with CAN ID 0A0 contain our speed data. This data is presented to us in the 5th byte of our packet's data field. Or maybe it's byte 4, depends if you start your count at 1 or 0. Now, what made our data so easy to pick out was a number of factors. First, the address, or CAN ID, was frequently updated. Second of all, the CAN ID 0A0 is a particularly low CAN address, as compared to the rest of the messages flowing over the CAN bus. On the CAN bus, the lower the ID is, the more important the message is. Like speed, for example. Lastly, the values in this portion of our 0A0 packet coordinate linearly and promptly with our speedometer. Now, with all this in mind, all we need is a microcontroller with a CAN transceiver, and a program that does the following. Our program must be able to look for messages with CAN ID 0A0, it's got to be able to parse out that 5th data byte, it has to then store that data byte as a mile/hour value, and it has to output that byte as binary over 8 parallel data lines. Finally, now that our remaining objectives are clear, let's knock this thing out. Now let's go forth and conquer in the vast expanse of knowledge.
I think that was your best one yet.
In our project's current state, we have our Game Boy and our control board. Now, I've been talking a lot about how the Game Boy receives data over this 8-bit port. But how does this interface work? Well, each of these 8 pins represents a binary digit. 1, 2, 4, 8, so on and so forth. Also, each of these pins is tied to a resistor that's leading to ground. That way, they're always in a low state by default. Now, if one of these pins receives a high signal, that pin is going to correspond to a bit in our speed value, which is only 8 bits long. That bit will be set high, and with all those 8 bits in our byte added together, that will produce our speed value. Here, let me demonstrate. Oh, please excuse the crudity of this model. I didn't have time to build to scale or paint it. We'll supply her 5 volts there. There. In short, these 8 pins correspond to these 8 numbers, and any combination of these values can give us a number between 0 and 255. So you got your 1s, your 2s, your 4s, 8s, 16, 32, 64, and 128. And adding them all up gives us 255. It's just fun to play with. Well, with that out of the way, we're going to need a device that sends those high and low signals over our 8-bit port. So I think one of these should do the trick. It's an Arduino Uno. I chose the Arduino Uno for a number of factors. It's readily available, easy to program, and it has plenty of modules that you can just plug right into it, like this can shield. Another reason I chose the Arduino is that there are plenty of libraries out there capable of driving this MCP2515 CAN transceiver chip. This should make things super straightforward to interfacing with our CANBUS, parsing packets with CAN ID 0A0, decoding our speed data from the 5th byte of that packet, and sending everything over to our Game Boy control board over that 8-bit port. Next, here's how I plan on connecting the Arduino to the control board. Here we have our data wires coming out of our 8-bit port. I've plugged the 6 first bits of our data port into analog pins A0 through A5 on the Arduino. That's backwards. That was also wrong. It gets a little confusing with all the wires that we have to manage. But our last two data lines, 7 and 8, go into digital pins 4 and 5 respectively. Unfortunately, due to the CAN transceiver using lines on both port A and port B of the Arduino, I can't just plug all 8 data lines from the control board into one of the ports on the Arduino, and thus I can't really use direct port manipulation clean and effectively. So that kind of leaves us with our data lines scattered all across the Arduino to open pins that I found, which included the analog lines, since we're not really using the analog functionality of the Arduino. I'm now going to be connecting our CAN connector up to our CAN shield. Gotta connect up our ground wire. And I'll be attaching this 5-volt line and this ground line to the Arduino as well. That's right, our CAN transceiver and our Arduino are also going to be powered off the Game Boy. And finally, we're done all the hardware for this project. This means we only have one more step, and that's writing the Arduino code. The code for the Arduino is in a sense similar to the Game Boy program, in that it's written in a dialect of C, it's pretty short, and it's easy to follow. First, we're including the Arduino SPI library. This is because the MCP2515 chip communicates over SPI. Then we include this MCP2515 library. This is the one written by AutoWP if you look it up online. Then we make a struct containing our CAN frame named CANMessage. Hey, Future John here. I botched the explanation of this line, so I'm gonna say different words. CANMessage is just a way to access our CAN frame struct in our MCP2515 library. This is gonna come in handy later in the code when we have to read data within our CAN messages. Then we have this line here. Basically, it's creating an object called MCP2515, and that object is a representation of our CAN transceiver chip. The 10 here tells our library that our MCP2515 chip's chip select line is connected to pin 10 on the Arduino. Basically, this allows you to connect multiple CAN transceivers up to your Arduino, and have the library figure out which one you want to talk to based on the object name. Then we have our setup function. We're configuring these pins as outputs. Pins 14 through 19 on the Arduino are another way of saying pins A0 through A5. And of course we have our standard digital pins 4 and 5. After that, we reset the CAN transceiver, tell our program that we're receiving CAN data signals at 500,000 baud, and letting our program know that our MCP2515 is clocked at 16 MHz. And then we set our MCP2515 to normal mode, because strange mode is out of the question. After that, we're making a byte variable called mile/hour, and that's a global variable. And then we've written this function called bitPrinter. How this works is simple. We start out with a for loop here that iterates through numbers 14 through 20. Wait, this is wrong. Okay, that's better. So it should iterate from 14 through 19. since 19 is less than 20, which corresponds to our pins 14 through 19 up here. Now let's break down this line here. This function here, bitRead, takes our mile per hour value, let's say 5 miles an hour, and converts it into a binary array. Next, it'll look through this array at this index, which is the pin that we're currently on, minus 14. Then when it finds the bit at that index, it'll write it out to the current port number that we're on. So maybe we're on pin 14 first. It'll do 14 minus 14, which is index 0. It'll see this bit, and then write it out to pin 14. Or the arrow the other way. Then we increment I, we're on pin 15, we look at index 15 minus 14, which is 1, and then output that bit at pin 15. And then wash, rinse, and repeat all the way through pin 19. Then, after we're done with this for loop, we do something pretty similar, except instead of iterating through, we pretty much do the same functions, but for pin 4 and pin 5, which look at positions 6 and 7 in our array. And that's how we get our mile per hour value into an array of bits that are then output over 8 separate pins on our Arduino, and having that Game Boy control board receive that data from those 8 pins. Finally, we have our main loop. We start out with this if statement here, and that only really does 2 things. It checks that we have a valid CAN message, and executes this code only if CAN ID is A0, or 0A0, it's just missing the leading 0 here. If both of these criteria are true, we set our mile per hour variable equal to index 4, or data bit 5, of the data field of our CAN message. And then we call our bit printer to print out our mile per hour value. Now that we have all our code written, it's time to upload it to the Arduino and go out for a field test.
Hoi mate, how's it going? Welcome back to Trash Time. And here we have a perfectly cromulent nugget. It's a Hyundai Santa Fe. And we'll be connecting it up to our Game Boy. Sorry, Wade. Big fan of the channel. Okay, now here's my setup. We have our OBD2 cable running out of here, and that goes over here into our CAN transceiver, then our microcontroller, into the control board, and over to the Game Boy. Now, this is actually my second time trying to film this. You see, the first time I tried to set it up, it looked like this. We have our OBD2 plug down here, that's running up here to the CAN transceiver and microcontroller, that then connects to our control board, and over to our Game Boy, which is being filmed by our DSLR. This setup was really bad because I couldn't see the Game Boy. I would have had to review the footage afterwards, and the footage was awful. So I built this jig here from spare parts I found in my shed, and now we should be able to actually see the screen on the Game Boy. Alright, so first thing we're going to do is turn the camera on, hit record, now the flashlight, and we'll turn on the Game Boy. And now we'll start the car. And here we go. We'll do a short drive around the block. Putting in reverse. Works in reverse and forward. And here we go. Currently cruising at 20 miles an hour. Well, that doesn't look right. It's 35 now. And yeah, that doesn't seem right. Now we're doing 15 here, and yep, that doesn't seem right. Alright, so let's head back and see what's up with the Game Boy here. I think it might be a programming error. Alright, let's get this sorted out! We're getting good speed data from the car because the values are going up and down in sync with the speedometer. So it's gotta be a data encoding issue? It's gotta be the way the data's encoded. It doesn't seem to be an offset issue, so it's gotta be a scaling issue. Okay, just who makes this car? Hyundai. And where in the world is Hyundai located? Korea!
Now, let's talk about South Korea. Can we talk about South Korea, please, Mac? I've been dying to talk about South Korea with you all day, okay? I was doing a little bit of digging on Wikipedia, and I found that in 1959, South Korea signed the Meter Convention Treaty that was then put into act in 1961. It's connected. Now, 2010, the year of our Santa Fe, is a bigger number than 1961, which means when this car was made, South Korea was using the meter, and still is, presumably, and subsequently, the kilometer. Now, time, it's metric, which means that South Korea believes in the hour, so they can measure things in kilometers per hour. Furthermore, miles don't exist in South Korea. There's no miles per hour? You gotta be kidding me, I got boxes full of miles. Now, to back up my Korea, Now, to back up my Korea doesn't use miles per hour hypothesis, I Googled, does Korea use miles per hour? And guess what the answer was? No! This means the speed data coming out of our car is in miles per hour? No. Kilometers per hour. That's gross. So our teeny tiny bug will definitely be obliterated if we take this line of code here and append times 0.62 on the end. Finally, converting our speed data into freedom units. He's gone mad. Ah! All right, here we are. We're back in the car. We've got the code updated on our Arduino, so let's see if it works now. Let's start from a complete stop, and here we go. $20 miles an hour. Turn here. Try somewhere closer to 10. And we're showing a little over 30 on the dash. 35. Yeah, it works. The digital dash works. We're cruising down the road. We're doing about 40 miles an hour. And yeah, it looks like it's coming up on the screen. Yes! All right, I'm gonna pull over real quick and try something. All right, I don't know if you guys can see this as well as I can, but we have our speedometer down here and our Game Boy over here displaying the speed data. Now, the Game Boy's display might look a little bit washed out from the camera's perspective. It does from mine a bit, but I can read it pretty clearly. But yeah, this means we've done it. We've made the world's worst digital dash. It's working great. It's displaying the speed data. It's updating really fast. And I'd call this project a success. And there we have it. A really stupid idea leading into months and months of work and culminating in the world's worst digital dash. Well, it's been one heck of a journey getting here, but maybe the real digital dash is the friends we made along the way. What, do you think this was the end of the video? Do you think I'm really happy with this clutched together mess sitting in my car? I mean, we got wires popping out all the time, the socket for the ROM chip's flaky, and just take a look at the edge connector here. It's completely tarnished and makes terrible contact with the pins inside the Game Boy. I mean, it's pretty okay for a prototype, but it's not something I'd want to end the video on. Let's just move this out of the way. So, in the end, I cleaned up everything a little bit and made a proper version 1. See, isn't that better? Look how much more clean and tidy everything is. I started out by taking our cartridge edge connector piece and making that its own separate module. See, it's so much neater going into the Game Boy now. And it's got this nice big box connector that you can just plug right into the top. That's right, I bit the bullet and sent some Gerbers over to China, a la JLC PCB. After that, I reworked the main interface board to make it a double-sided construction, which makes this so much smaller and reliable. Also added the ZIF socket up here so that you could change out the ROM real easy. Then I made this last board here at the lab. We have an Arduino Nano, one of these tiny CAN modules, a voltage regulator so that all of this could be powered off the car instead of the Game Boy's batteries, and one of these DB9 connectors. Which means now I can use one of these DB9 to OBD2 cables, which, side note, doesn't seem to have a standard pinout. I've been told the pinout for these cables is really inconsistent, like this will not work with this module up here. So I had to use a multimeter and buzz out the pins on either side to figure out the pinout for the DB9 connector. I mean, the OBD2 one is a standard, so I just had to figure out where the CAN high, CAN low, ground, and 12-volt lines went on this side of the connector. So yeah, I built this first one and it works okay, but I found it still to be a little too disjointed. So I built the second one. It didn't work and sank into the swamp.
So I built a third one. That burned down, fell over, then sank into the swamp, but the fourth one stayed up.
And here it is, the fourth and final version. Though it's technically version 3.1. You can see where the ROM chip goes here, the Arduino Nano over here, and the CAN transceiver over here. Oh yeah, by the way, the only modification I had to make to the Arduino code was changing the clock speed of our CAN transceiver from 16 MHz to 8 MHz. And yeah, that's literally it. Also, as a new function, I did this power routing switch matrix so that this board could be powered by the Game Boy, or it could power the Game Boy if the Game Boy didn't have any batteries, and it supports the original 6 volts that the Game Boy uses, or the 3 volts that the Game Boy Pocket uses. And once again, we have that nice DB9 connector on the end. See, look how sleek that is. But, can it be sleeker? Turns out, why use wires at all? I present to you the all-in-one. Yeah, it's just these two boards soldered together, which I guess technically makes this its own cartridge. Yeah, this is just dumb. Then again, the whole notion of using a Game Boy as your car's digital dash is ridiculous. Which is why I'm glad this is the final form of the Game Boy Digital Dash. Anyway, here's some footage of the last version of the Game Boy Digital Dash system. Alright, here we are rolling around with the final iteration of the Game Boy Digital Dash project. And yep, it's gosh darn near impossible to film. Yep, it's really difficult to film. Yeah, it's displaying the speed data pretty well, and actually it's really easy to see at this angle. But yeah, I think the camera's just picking up a bit too much glare. This is like the worst thing in the world to film. Tell you what. Now, another great feature of the Game Boy Digital Dash is it doesn't have to work with just the original Game Boy. Yep, we also got it working on the Game Boy Pocket. And again, it's looking like a glary mess on the phone camera, but I'm not having any trouble seeing it. Oh my gosh, this is the end of the project. I started this back in July of 2024. I haven't changed my clothes in 6 months. I got fat! Thank you all for watching, and if you enjoyed the project, please subscribe for more. Links to the various project files will be in the video description. I also find it extremely important to cite your sources, so here are mine. Starting out, we have Mark Rawer's The Game Boy Project. This PDF was a great jumping off point, and I'm really glad I found it. We also have the Game Boy Programming Manual, version 1.1. This came in handy for figuring out how the memory map for the Game Boy worked. I guess I'd also cite the Game Boy Development Kit 2020 GitHub repo, since I recall they had pretty good documentation, and it's just a really cool project. Also, shout out to the channel Gaming Monsters for making a great crash course on GBDK 2020. And just as a good book recommendation, John Uffenbeck's Microcomputers and Microprocessors, 2nd edition. This is just a good resource on its own. It helped me understand how bus transceivers work and how communication happens within 8-bit microcomputers, like the Game Boy. Finally, I'd like to give a shout out to all you guys watching these videos out there. I like to teach and do cool projects, and this is the perfect excuse to do so. So yeah, thank you all out there for enabling this crazy hobby of mine. So take care, and I'll see you next time.